Good morning, my lovely 13ers. Right, buddies, here we go, our next lesson on second order differential equations. How exciting. So, yeah, pretty much last lesson, what we discovered is there was a great big shortcut which was called using an auxiliary equation to solve these linear, homogeneous for second order, what's the other thing, constant coefficient, differential equations. How exciting! Where a, b, and c were constants. We came up with a shortcut way of doing it. It involves something called an auxiliary equation. So this is the general form, don't forget, of the ones that we're solving. And it had an auxiliary equation of this. So pretty much bin off the d squared y by dx squared and pop a lambda squared in its place. Same with dy dx, pop a lambda in, and then c, oh shoot, I shouldn't have a lambda, whoops, 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 whoops. I'm glad I spotted that. And yeah, same deal with the c, but it's not going to have a anything on it. So there you go, like a beast. So there we have it. Yeah, cool, and it made this as an auxiliary equation. Now, here's the thing, you then solve the auxiliary equation, and what we discovered last time was that you'd get two answers out, lambda 1 and lambda 2, and they ended up being put into the general solution like this. The general solution was some constant times e to the lambda 1x plus some constant times e to the lambda 2x. Your two roots were represented there. Your two, what's called complementary functions then, get added together to make your general solution. So both of these, the a e to the lambda 1x and the b e to the lambda 2x, both solve the differential equation. So to get the full, scope of everything, that's the full answer to the differential equation, it's just the two of them together. Now, I didn't tell you this last time, but we solved all these ones that were b squared minus 4ac is greater than 0. In other words, ones where the discriminant is positive. In other words, they were all for ones where there were two roots. Okay? I bet you can see where the whole rest of this unit is about to go now that I've just said that. But yeah, so let's do it. Is that the only thing that could happen when you try to solve an auxiliary equation? Well, no. Because here's another thing that could happen. You could get b squared minus 4ac equaling 0. So while your answers are real answers here, and, well, here as well, this one's actually got an answer of 0 coming out. Now, if lambda is repeated, the general form is that, okay? And this is really the only thing that you really need to know, but instead of just calling the lesson there and doing one practice question and leaving you guys like an hour to actually practice and get good at it, no chance. I'm going to do a whole bunch of evidence and proving and stuff with you to see why this is the case. But you'll have to take my word for it now, so put this as a note. It's, if the discriminant is equal to 0, then the general form of your differential equation is going to be a plus bx e to the lambda x. Okie doke, my buddies. So that is the new thing. Now, I'm not going to prove this because actually one of the questions that I set in your homework set is actually to prove it, and it helps you. Like, it tells you steps along the way, and I thought you might want to do it, so I won't spoil it. But the textbook, without proving it, had quite a nice argument, which wasn't really fleshed out enough. So I've done the textbook argument with full kind of steps, so you can see what's going down. Cool. So yeah, there, I wrote it there as well. Oops. Question 11's got the proof if you want to try it. Okay, I'm going to just try to show you that this is going to be the general solution, okay? That's what I'm going to try to show you, but I'm not going to actually prove that it is. I'm just going to evidence it. So let's do it. Okay, so there we are. That's our standard form that we're in right now of the type of differential equation that we solve. Cool, cool, cool. Oh, and if you want, you can pause and try to get ahead of me, but I wanted to go quick. That's why it's all written out already. I'm just going to delete rectangles. So if you want to try to be ahead of me and write it down, that's okay. And it's probably not a bad shout, actually. Or at least copy down and be like, oh yeah, I see where that's come from after you've seen it. But yeah, here's your general kind of form of it. Now, that leads to this as the auxiliary equation, which is no trouble at all, which means, my buddies, what we're going to do is we're going to solve it. Now, we don't have any numbers, because a, b, and c are all unknown, so the only way we can solve it is with what? That's right, the quadratic formula! Boom! So that's how you solve it. And conveniently, they're a, b, and c, so the quadratic formula is as you've always known it. Cool. Now we are trying to prove one for a repeated root. That's a given, okay? We're trying to prove for a repeated root, which means that the discriminant's going to equal 0. So the square root bit is going to be gone, which means the general solutions, or the root, the repeated root, is lambda equals minus b over 2a. Okie doke, that's going to be the root. That's the actual answer to the auxiliary equation. Now, here's the thing though, we're in a bit of a pickle here because second order ones have to have two parts to them. So remember how it used to be a e to the lambda 1x plus b e to the lambda 2x? It was two parts in it. The first order ones only have one part, but what on earth are we going to do here, buddies? Because if you look at it, like, yeah, we're a bit scuppered here. I'm just going to show you. Certainly that's going to be a solution, okay? A e to the lambda x, so like where it's that, but don't worry about that. A e to the lambda x, you'd expect that because that's in keeping with the last lesson. But what on earth are we going to do for our second solution? Because we don't have two lambdas, so we can't be having like b e to the lambda 2x. Well, I'll show you, buddies. What we're going to do for our second solution is we're going to pop an x with the b. So you'd think it should be be to the lambda x as well, but there's actually a problem with that. What do? We introduce an x. Now when you do the proof, you'll see why, but I'm going to show you it works with evidence. Cool? So bx e to the lambda x is what we're going to use as our second solution, as our second complementary function. So it'll be this added together with that in order to make it. But you'll be sitting there thinking to yourself, oh, why didn't you just use b e to the x? You'd be thinking to yourself, you'd be thinking, why not b e to the x is exactly what you're thinking. Well, here's why, buddies. Because if you use b e to the lambda x, like binning off this extra x, which seems made up, it seems ridiculous that we just popped an extra x in there, why wouldn't you just do this? Have a different constant timesing by the e to the same root. Well, check it out. Look what you could do if you did that. If this were the case, so it was this red one and this one, well, here'd be the general solution then. It would be the two of them added together. But then I can just factorize the e to the lambda x out, and then you're left with a plus b in a bracket. But a and b are just constant numbers, right? They're not like functions of x or anything. They're just constant numbers. That means I can just say, well, if I have a constant with another constant, may as well just call it a third constant, c. And then look at that. It becomes c e to the lambda x. But oh no, that's only got one component. So that's a first order solution, not a second order solution. So we broke it. So how do we fix it? By introducing this x. Why? You'll see in a minute. Okay, so it becomes this, buddies. A e to the lambda x plus bx e to the lambda x, which puts this as the general form, which you will memorize and which you will be using all the time. Now, I still haven't given you evidence. I'm going to show you why this is the case, okay? So there's where it comes about. This is why it's the general solution, and this is now why it works. Okay, here is your general form again, and here is the auxiliary equation. Now, both of our two answers, okay? Both of our two answers of the a e to the lambda x and the bx e to the lambda x should solve the differential equation. But the bx e to the lambda x is the suspicious one, right? We think that the other one's okay, or we should, because it's the same as it was last time, and they were working last time. So we're going to have to check out this bx e to the lambda x one. How are we going to do that? It's right back to the first thing that we did in the first unit. You're going to just, well, you can pop bx e to the lambda x in for y, and then if you can get an expression for dy dx and d squared y by dx squared, and pop all them in together, you should make an answer of 0. That's how I'm going to give you evidence. So, let's do it. Dy dx then, if you're checking this one, the suspicious one, it's going to become this, and that's because of chain rule. So when you're copying it down, or not product rule, I mean, and chain rule, haha, I wasn't all the way wrong, it's from both. So when you're copying it down, just confirm that you get that also, okay? Dy dx should be this, okay? It's differentiated of the one that we're testing. Cool. Second derivative is a little bit harder, but not too bad. It's chain rule and product rule again. The first one is not too bad, and then product rule on this majestic piece there. It ends up becoming this, which is a little bit untidy because these two are the same. So the first two are the same. So that. Cool. So what you can now found then, my buddies, is that we've got an expression for the derivative and the second derivative. Now I did say how we were going to show it, how we were going to evidence it, how we're going to kind of prove it. What I guess it does prove it, but it's not a, yeah, it proves it assuming that this is true, which I don't know, which I suppose yeah, it is a proof, I suppose, that we're doing. It is qualified as a proof, but it's funny that we've just come up this out of nowhere. That's what's weird. Okay, so here we go. How are we going to check it? Well, we're going to pop them into here, and we're hoping that 0 comes out. So considering the left-hand side of equation 1 of the general form, you're going to get that. Okay? That's it with them all popped in, okay? So A, B, and C, you can see them in the front, and then you've got that. Now, I went mega lazy here because I didn't want to times them all out because I felt like I was writing too much at this stage, and so I've done a couple things to get it to turn into that. I'll tell you really quick, though. I did two things at once. I timesed in the A, and I timesed in the B, and I timesed in the C mentally, and at the same time I factorized out a BE to the lambda x. So if you check it, every single term has a BE to the lambda x in. So I factorized it and times the A in the same go. So just for the first term, just so you can see it, there's the B and the E to the lambda x. Take them both away, pretend that they're outside. And what are you left with? Well, a 2, an A, and a lambda. Hence the 2A lambda. And the same deal here. A lambda squared x, blah, blah, blah. Cool? Right. It's still horrendous, but I know I'm trying to make an answer of 0, right? And I see that there's x's in it, and that's a bit weird, but I see that there's lambdas in it, and that's a bit weird too. So here's what I do. I'm just going to show you and see if you can get it. I'm going to factorize the x out inside the bracket. Can anyone see something clever? I'll give you a hint. I underlined it in blue. What's going on here? What is that? What's going on, my buddies? A lambda squared plus b lambda plus c. Oh my gosh, it's the auxiliary equation! And what does the auxiliary equation equal? 0! Oh my gosh, it's equation 2! So we've got equation 2 to fall out, the auxiliary equation equaling 0. How exciting! So that is phenomenal, isn't it, my buddies? So if that's gone, you're just going to be left with that. Cool? Because that was the auxiliary equation. It did equal 0. That's just a fact of the matter. That's what it is. That's how auxiliary equations work. Cool. So that's what we've got is just this. But then also, I don't know if you remember this, remember when we presumed that the repeated root, or we presumed it was a repeated root, and that gave our solution of minus b over 2a? See what I mean? That is what lambda is. Yeah, because it was a repeated root, and so that went away. So there only is one solution, and that's lambda equaling negative b over 2a. Well, check it then. If lambda is minus b over 2a, here's what you can do. You can bosh it in. Cool? So check it out. 2a and then lambda is minus b over 2a. Cancel, cancel. You're left with minus b plus b, which is 0, which is the right-hand side. Oh my gosh, we proved it, my lovelies. So by using y equals bx e to the lambda x, and then doing all the differentiating rubbish with it, we have verified that the left-hand side of the equation does indeed become 0, which means that bx e to the lambda x is indeed a complementary function and indeed does play a role in the general solution then. It is a solution in its own right, which means the general solution is going to be these two bits together. This bit, the a e to the lambda x, and the bx e to the lambda x are going to go together to make this as a general solution. And that's what I got. So there you go, buddies. So y equals a plus bx e to the lambda x. Cool beans? Right. So all of that behind us, how many minutes was that? 14 minutes worth of that. We can actually try to do a question now, and we'll just do this one. It's not too bad. It's the same as the last topic, so let's have a go. Okay, so here we have it, my buddies. Let's have a go. Okay, I'm only just doing this one question with you. It shouldn't be too bad, though. So it says, find the particular solution of that equation subject to the conditions that were z, oh, I hate it when it's not y's and x's. When z is 0, dz dt is 5, when t, and z is 0, and dx dt is 5, when t is 0. Cool. Right then, let's get on to our general solution first. So what we're going to do is we're going to pump out our auxiliary equation straight away, okay? We're cutting to the chase. We're not doing any of this stuff that we did last week. Let's just get to the chase here. Lambda squared plus 6 lambda plus 9 equals 0. Yeah? because I've just put my lambdas in. Lambda squared, lambda, and nothing. Cool. So what are we going to get? Two numbers that times to 9 but add to 6. Oh my gosh, it's 3 and 3. It's a repeated root. Imagine that. So it's x plus 3 squared is what that's equal to, which means lambda equals 3 only. It's repeated. Got me, buddies? It's on. Oh, drat, it's not that. I was just joking. Just seeing if you're paying attention. Minus 3, I meant to say. Minus 3, repeated. So yeah, brilliant. So that's what we got. So what are we gonna do with that then, my folks? If that is our lambda, well, we can go right for our general solution. Because we knew in our general solution that it was going to be this. It was going to be y equals, of the form a plus bx e to the lambda x is the form of our general solution. So in our case, where y is z and x is t, it's going to be z equals, and it's going to be a plus bx. Oh, no, it's not a plus b t, I should say, even. A plus bt e to the minus 3t, I believe. And I think I'm happy with that as my general solution. Is that cool, my buddies? Okay, good. So if that's the general solution, now we're going to have to find the particular one, aren't we? So let's go for it. We got to get what a and b is if we want the particular solution. So let's go for the particular, okay? Particular. Okay. Particular. Let's go with the first condition first. First condition is at t is 0, z was 0. Okay, so let's see what we get off that. We're going to get 0, so into the general solution, equals a plus 0 e to the 0, which means 0 equals a times 1, 0 equals a. That means a is 0. Oh, yeah, I've already written it now, which means a is 0. 0 is a, means a is 0. How exciting. Okay, and to get the other one, we got to use the other condition. We're going to use the condition that at t is 0, that dz dt is 5. Okay, so we're going to use that condition too. So let's do it. dz dt, differentiate it first, is going to equal, okay, I know a is 0 already, so I'm thinking to myself, let's cut to the chase. I'm going to. I'm lazy. I'm sorry, my lovelies. I'm a bit lazy. A is 0, right? I don't want to have to go through all of this palaver if a is 0. So let's start off like this. Z is then going to equal 0 plus bt e to the minus 3t. Sorry, did you get what I was doing there? I didn't want to do all the differentiation if I didn't have to. I found a shortcut, so I changed my mind and I went for it. So z equals, and this is going to be just bt e to the minus 3t, because the a one's defo is gone because it's 0. Okay, alright then, so now we can do our dz dt, so whoop, up here, dz dt is then going to equal, it's going to be chain rule, or product rule I mean, so differentiate the first, bt is just going to become b, leave the second one chilling, e to the minus 3t, plus, leave the first one chilling, bt, differentiate the second one, it's going to be minus 3, I'm going to put it first as well. You guys are good. I can cut steps because you guys are good. I'm going to pull the minus 3 first, and it's going to be bt, and it's going to be e to the minus 3t. Okay, so in case you didn't see it, leave the first two chilling, bt are chilling, and then the minus 3 is going to come down with chain rule. I put it first rather than directly in front of the e to the minus 3t, and that's what you got. Cool, now we're going to use the condition, okay? So it did say that dz dt was 5, so it's 5, and it said that t was 0. So this is going to be b e to the 0 minus 3. Oh, well, this is all just going to be 0. Minus 0, because there's a t there. Cool, so it's all going to be 0. Which means that we're just going to get b equals 5. Like a boss. Cool, which means our particular solution. To answer part I, our particular solution is just going to be z equals, A is nothing, so B was 5. It's going to be 5t e to the minus 3t. There you go. That is it. So that is our general solution, and yeah, I guess that's our general solution. I don't have anything else to say about that. Hooray! Cool. Double I. Sketch the graph of the particular solution. Okay, so these are always a little bit fiddly and faddly, my lovelies, but at the same time, you do have a graphing calculator, but I can't be bothered, so let's do a good estimate of it. And it is, bearing in mind I do know what it's supposed to look like from the textbook as well, but we can logic it. So you guys ready? So to start with, I have a point, okay? I'm going to put that on. T, so this is T, and that's Z. I do have a point, 0, 0 it goes through, definitely, okay? 0, 0 it goes through, it's given. And you also know that at 0, dz dt is 5, which means positive gradient. So we've got that, okay? So I've used that. Here's how did I do it again? Because I have that point, and I also know positive gradient at 0. So it's at least going to start by going up. That's how my logic works. Okay, next thing I like to consider is the extremes, because that's always a great shout as well as what to do. So I know that z is equal to, I'm going to rewrite it in a different manner, 5t over e to the 3t. Okay, so that's it. Now what are you going to do with this? What grows faster, 5t, which is linear, or e to the 3t, which is a crazy mentally quick exponential function that goes like mad? Which one grows faster? Something linear or something exponential? That's right, exponential. So basically, if you took the limit then as t goes to infinity, this is writing it poshly. All I'm saying is big pause right now. If you take the limit as t goes to infinity of z, or of, let's do the whole function, of 5t over e to the 3t, well, you're going to find that it converges to 0, okay? Because the bottom's going to get enormous. So it'll be a number, at the end of the day, just imagine it being a number like 500 over 500 million. That's like nearly 0. So it is 0 at the extremes, at infinity. Which means our graph is going to look something like this. It started with a positive gradient. It's going to be a curve because it's not a line. And so it's going to be a curve, and it's going to have to become asymptotic down here. So it's going to be like that. Cool beans? That'll be enough to get full marks on it. And that's cool. I think that that's enough information, and you've got your lovely graph drawn. So I hope that that's okay. See, the actual, this is what you have to actually practice now. So this isn't too bad. It's the trying to prove it and stuff that's a bit tricky. And here's what I'd suggest then. Page 263, 5 to 11, do a mix though, okay, buddies? Because they are varied in difficulty. Question 11 is the nightmare one. I haven't actually tried it myself, to be fully honest, but question 11 is actually the proof, the full-on proof, not like knowing what the answer is and then proving the answer is right, but proving from scratch is question 11. So if you want to try that, that's cool. I wouldn't spend all the whole lesson on it. I would certainly give myself a bit of a mix though, because you do have to have your head around this, as well as the old format as well. So these are not all repeated root. Some of them are so they won't all be of a plus bx times e to the lambda x. Some of them are a e to the lambda 1x plus b e to the lambda 2x. Cool? You just have to be alert as to what's going on. Cool beans, buddies! Whew! So that's it from me. Knackered now. Ooh, big long lesson again. And when you're all done, put it on Show My Homework, and I shall see you for next lesson. Bye, buddies!